Hello, thank you for joining us on our magnetism notes. If you want to look over the notes that you did in class, or if you haven't done these notes in class, it would be a good time to do them now. Or you can sit there and listen and learn from the PowerPoint. So, let's get started. A couple little general pieces about magnetism. They were originally discovered by the Greeks about 2,000 years ago, and they called these magnets lodestones. And they found out that these certain rocks and minerals had unique properties in the fact that they would attract or repel certain metals, and they were also very good for use in navigation. So as you see, this thing I have over here is a lodestone that was cut in a certain way so that it can rotate on this plate, and whenever it rotates, it can point to the magnetic north, which is very good for navigation. So that's one use of these lodestones that the Chinese used, and actually a lot of people use these lodestones to navigate ships. And these lodestones were generally some sort of iron ore, so that was a good thing. And then we have our magnetic poles. These are regions of the magnet that produce a magnetic force. The pole pointing northward is the north pole on our magnets, and the pole pointing southward is the south pole on our magnets. Not true for the north pole and south pole of the Earth, but we'll get into that at the very end. But the pole that points north is the north pole, the pole that points south is the south pole. And if you take a magnet and you break it in half, it does not create just a north pole magnet and a south pole magnet. No, it creates two separate magnets. So two separate magnets that have a north pole and a south pole. They're just smaller magnets. So a lot of similarities between magnetic poles and electric charges, but there's one difference. So let's look at the similarities. First off, up here at the top, over here, the magnetic pole and electric charges, likes repel and opposites attract. So that's the same as it was with our electric charges. Magnets work in the same way. Also, right here and right here, forces act over a distance. So the forces don't have to be touching for that force to be applied. They can act on each other over a large distance. But the one main difference is that you can separate electric charges, but you cannot separate poles from each other, magnetic poles from each other. So that is one difference that there is. All right. Couple, interesting properties about magnetic fields. The space around the magnet creates a magnetic force, and you can see it with these iron filings on this paper. So if you spread out these iron filings on, some sort of white paper is nice, you can see the magnetic fields moving from North Pole to the South Pole. On the picture on the left, on the picture on the right, you just have one pole that's touching the paper, and it seems to be repelling all these magnetic filings. And just to reiterate what we talked about, magnetic fields are very similar to electric fields, even in the sense that these field lines are relevant to magnets and to charges. So right here we have our magnetic field, and it's going out of the north and into the south. You can see the arrows coming out of the north and they're going into the south, much like over here where we have the electric field lines going out of the positive into the negative. So the same concept works in both of them. And also remember, the more lines, the stronger the field. And the field is always strongest right here at the poles, because you can see there are more lines right there than you would say right here. Okay, so the poles are the strongest, and you can tell that because there's always more lines right there. All right. So what creates a magnetic field? Well, it's moving charges. So these electrons that spin around the nucleus, they don't just rotate around the nucleus, but they also spin at the same time. And these charges that are moving create a magnetic field. So most materials are not magnetic because the electron pairs cancel each other out in the magnetic field. So there's all these electrons moving around, and because a lot of times there might be electrons going this way and electrons going this way, electrons going this way and this way, all these magnetic fields ends up canceling each other out most of the time. And you can also think of an electron as a tiny magnet. But if you can get a lot of electrons to spin in the same direction, like so, something like this, then that's whenever you can make a good strong magnet. And if the spin is, one is going, this direction, and then there's another one going the opposite direction, that's a terrible picture, but you get the point. If the electrons are moving in opposite directions, the magnetic fields cancel each other out of these electrons. All right. Iron, nickel, and cobalt. These three materials are materials that have extra atoms. So these three materials right here, iron, nickel, and cobalt, they have extra atoms in, or sorry, not extra atoms, they have extra electrons. So they have electrons that are not paired with a proton, and these extra electrons are very easy to manipulate. So it's very easy to make these extra electrons move in the same direction. And if you can get more electrons moving in the same direction, you'll be creating a good magnetic field. And one reason why iron is such a good magnet is because it has 4 unpaired electrons. Those 4 electrons are very easily manipulated. And if you can manipulate those 4 electrons in one atom, and you have billions of atoms in a piece of iron, that would make billions and billions and billions of electrons that you can move in one direction, and thus making a nice magnetic field. Alright, so we need to talk about magnetic domains. So these domains are large clusters or sections of a material, and the atoms are aligned in a certain direction. So up here on this first picture, these domains are all pointing in different directions, and because these domains are pointing in different directions, the magnetic field in each one of these domains here, the magnetic field in each one of these, see the arrows going in different directions, that represents the direction of the magnetic field. And they're all going different directions, so all these magnetic fields are canceling each other out, so therefore this material up here is not magnetized. But down here in this picture, all the domains have the arrows pointing in the same direction. So therefore, all of these, because all these domains are pointing in the same direction, that means that this material has become magnetized. So all the electrons are flowing in the same direction, which means that this material will become magnetized, so because all these electrons are flowing in the same direction. Alright, so magnetic domains can create a permanent iron magnet by placing the iron in a strong magnetic field. So if you get iron and you place it in a strong magnetic field, you can end up creating a permanent magnet. You can also create a temporary magnet by placing materials with iron in them near a strong magnetic field. But the thing is, if it just has iron in it, and it's not just solid iron, once that magnetic field is gone, the domains will revert right back to where they were, and the material won't become magnetized anymore. So you can make a temporary magnet by doing that. And you can also destroy magnets, permanent magnets, by dropping them. You destroy them by heating them up. Whenever you drop them or heat up a magnet, it causes those domains to be kicked around, and therefore they're not in alignment anymore. And what we have here is a picture of iron. Up here, the domains are all jumbled up. You can see the arrows pointing in different directions, so that's unmagnetized iron. The next picture down here these domains, they're starting to line up. They're not perfectly lined up. There's still some that are crooked and backwards, but most of the domains are in the same direction, so this is slightly magnetized iron. And then the third one down here is a very strongly magnetized iron, because you can see all the domains pointing in the exact same direction. So therefore it's very strongly magnetized. And then even if you break it in half, you still got two magnets, two separate magnets. They're just smaller. That's the only difference. They're smaller magnets. Alright, so if you were going to create an electromagnet, which is what we have in our picture over here, you can get some sort of battery source like this right here, and you can connect coils of wire to it. And when you connect those coils of wire to it, and it comes around some sort of iron core such as a nail, so you wrap it around here, and then you complete the circuit by sending the wire through to both sides of the battery, you can create an electromagnet. And in this case, this nail will become a magnetic piece of iron. It'll pick up metal, and if you happen to break the circuit somehow, it would drop the pins down, and therefore it will not become magnetized anymore. The reason why it becomes magnetized is because it has lots of moving charges moving in the same direction, creating that magnetic field. And this was discovered in around 1820 by a guy named Hans Christian Ørsted. This guy right here, Ørsted. So Ørsted discovered this, and he also found that reversing the current would reverse the direction of the magnetic field as well. So if you change the direction of the current, if you switched where the batteries were connected, if you made the positive negative and negative positive, it would reverse the direction of the magnetic field. So electromagnets are a current carrying coil of wire with many loops. So we saw in that picture the nail had many loops of wire wrapped around it. And electromagnets also have a north and a south pole. And the strength of an electromagnet depends on three different factors. And these factors are important. So the number of loops that you have will determine the strength of that magnet. The more loops, the stronger. The lesser amount of loops, the weaker the magnet. Also, the amount of current that is flowing through that wire. The second note here. The larger the current, the stronger the electromagnet will be. Also, the third thing is the presence of an iron core. If there's an iron core, then that means that it will be stronger. So if we have charged particles at rest, and that means they are not affected by a magnetic field. So all these, if charged particles are staying still, they're not affected by a magnetic field. And when the charges start moving, though, that's whenever you create a magnetic field. And technology like this was used in the earlier TVs to create the picture on the screen. And we have learned in times past that the Earth's magnetic field deflects these charged particles from outer space, and that's where we get our cosmic rays from, in the northern lights and the southern lights. So the Earth's magnetic field diverts charged particles from bombarding us in our atmosphere. It just ends up going to the north and south poles of the Earth. Alright, so if you have a current carrying wire and you place it in a magnetic field, that current carrying wire will be deflected. And if you reverse the current of the electricity in the wire, it will deflect the wire in the opposite direction. And you usually get the most amount of deflection whenever the current is perpendicular to the magnet. So they're 90 degrees to each other. You can get the most deflection from your wire if you place it in that magnetic field. Now let's talk about motors. This is very important that you know about motors. Motors have an electric current that run through them, usually through some sort of battery. And the motors will take electrical energy and convert it into mechanical energy. So if you have an electric motor in your car, it's taking the electricity from the battery, and it's making that energy from the battery, and it's making the wheels turn, which would be mechanical energy. And there's also lots of other different ways that motors are used to create mechanical energy. And coming back to Earth's magnetic field. So, Earth is a gigantic magnet, and the magnetic poles on Earth are opposite of what we call the North and South Pole on the Earth. So if you look at the Earth, the northern part of the Earth is actually the Earth's magnetic South Pole. Now we call it the North Pole, but magnetically it's the South Pole of the Earth. And the southern part is actually the North magnetic pole of the Earth. Now the reason why that is so is because whenever we have a magnet and we place it on the Earth and we say that this is the north end of the compass, sorry, this is a compass. So if we have the north end of the compass and we say that this line right here is this arrow right here is going to be deflected. Wow, this is terrible. Let me try again. So we have our compass. This is the north end of the compass, and we know that because it makes this arrow right here point towards the north. So this compass right here has, there we go, that looks better. So this compass is a magnet, and this needle inside is magnetized so that the north end of the magnet is actually attracted to the south end of the Earth's magnetic field. So we know that opposites attract, so therefore the north end of the magnet inside the compass is actually attracted to the southern part of the Earth's magnetic field, which is actually in the north part. So that is confusing, but it actually makes a lot of sense because opposites attract, and so the north end of the compass is actually attracted to the southern magnetic field, which happens to be on the northern part of the Earth. Wow. Cool. And we also have our right-hand rule. Now remember the right-hand rule, the direction of your thumb is the direction of the current. So the current is running up the wire in this situation. And we will put our thumb, and we use our thumb as the direction of the current, and we wrap our fingers around the coil or around the wire that is creating this current. And the direction that our fingers bend around the wire is the same direction of the magnetic field using your right hand. We call this the right hand rule.